Hello, my name is Professor Paddy Regan from the University of Surrey in the National Physical Laboratory, and it's my great pleasure to be giving you guys a little introduction and lecture to some useful, interesting applications of nuclear physics in our online seminar series next week. And hopefully this will encourage you to think seriously about doing physics at university, and specifically the University of Surrey. So I'm going to take us forward through this little presentation that I've produced, which is only take about 5–10 minutes, and it'll give you a little bit of insight for what we'll try and cover in our online lecture next week. So that's a picture of me, Paddy Regan. The thing I'm holding there is called a gamma ray detector. It's a specific module that allows us to see electromagnetic radiation that's emitted from the nucleus of atoms, basically the smallest things. And that really answers the question, as I have put that, answers the question there, that how do we see the smallest things? So matter is basically made up of atoms, and inside of those atoms are tiny, tiny atomic nuclei, and those nuclei are made of protons and neutrons, and how those protons and neutrons rearrange each other and excite each other and move around is out of the visible region that we can see with our eyes, but we still have developed over the years some very, very clever techniques to actually understand how those protons and neutrons interact with each other and basically what atomic nuclei look like. And the picture on the bottom left was to try and explain or shed some light on another interesting question or problem that we'll try and look at during the hour or half an hour or so next week, which is where do the elements of nature come from, the stuff that makes up everyday matter, where does it come from? And I'll try and show you some examples of some information that suggests very strongly that much of the heavy material, things heavier than iron certainly, that exist currently on this planet were formed billions and billions of years ago in very explosive supernova events in stars a long, long, long way away from the Earth. So let's carry on. Okay, so this is what I'm going to try and show you for a week. What are the fundamental building blocks of matter? How do you see inside the smallest things, an atomic nucleus? Where and when were the stable isotopes formed? How do you measure very, very long radioactive half-lives? If you want to measure the half-life of a radioactive piece of material that's longer than your half-life, your lifetime, and you can't wait for half of it to decay. So how do we do that? We need to know that information to age and date some of the oldest things, like the age of the Earth. And if I have a bit of time at the end, hopefully I'll give you some information about what are the applications of useful applications of nuclear science. So the pictures I put at the bottom there are a little cartoon trying to show you the different layers of the onion as to what makes up matter. The periodic table, which you should be all familiar with a bunch of elements in there that you might not have heard of at the top end. And then on the right-hand side, a sort of two-dimensional variation of the periodic table, which we call the chart of the nucleides, which shows both the radioactive and stable forms of matter. Okay, so what's matter made of? Well, you know this before. The word atom comes from a Greek word meaning uncuttable or indivisible. Atoms are, as far as we know, the smallest sort of elementary building blocks of matter that make up everyday life. They're of the order of something like 1/10 of a billionth of a meter across, 10 to the minus 10 of a meter, and they're surrounded by negatively charged particles called electrons, and those electrons interact to determine things like chemistry and how those atoms interact with each other. But most of the mass of the atom is in the center of the atomic nucleus. Nuclei make up a tiny, tiny fraction, sort of one part in sort of 10,000 or so, or 100,000 of the radius of the atom is made of the atomic nucleus. But in that atomic nucleus, something like 99.95% of the total mass of the atom is held. So nuclei matter, literally, nuclei are the matter, and they're made up of protons, which are positively charged particles, which have got a proton number Z, and that determines what the chemical element of that material is, and neutrons, which determines the mass. In fact, those protons and neutrons, we now know, if you want to go further, have got substructure. Protons and neutrons themselves have a substructure made up of stuff called quarks, ups and downs. So that's the realm of particle physics. They're interesting in themselves. We're not going to cover them in my lecture online, but they're the next layer down in the onion. An interesting thing about quarks is they can't survive on their own. If you try and pull them out of a proton and a neutron, it costs so much energy you start spontaneously creating more of them. So here is a periodic table. Hopefully you're all familiar with this concept. Periodic table is defined basically by how different elements chemically interact with each other, and the chemical label is determined by the number of electrons that go around the atom in its neutral form, and that's also equal to the number of protons in the middle of the nucleus. Interestingly, you can see here we've got a load of different elemental groups and tables here, but every element above element 83, which is bismuth here, so polonium, which is bismuth, element 84, all the way up to the heaviest element currently discovered, which is oganesson, element 118, are all radioactive. So they don't most of them just survive for a fraction of a second. They can still be made, but they don't make up the everyday material. So elements are defined by the number of protons in the nucleus. What about isotopes? Well, isotopes comes from the, again, Greek word iso means the same, topos like topography, where we get the word for maps from, means the same place, and these things mean protons or neutron combinations that have the same place in the periodic table but have different masses. So these are basically forms of the same element that have got different forms of neutron number in the middle of them. And these were identified first by famous chemical physicist called Aston, who used mass spectrometry, basically bent elements of the same material around a magnet and saw that they were separated out into different mass groups. So at the bottom there's an example. I've just shown some results of the mass separation of the natural element krypton, the gas krypton. You can see it's got elements ranging, it's got isotopes ranging from krypton 78 all the way to krypton 86, but there are gaps, krypton 79, krypton 81 and krypton 83, for example, which don't show up naturally in natural krypton, and that's because those forms of those krypton isotopes are radioactive. It means that they basically spontaneously radioactively decay to form another element. And that's based on nuclear physics. So we can build up a two-dimensional version of the periodic table called the chart of the nuclides. We can look and see what forms of elements exist in stable form. So hydrogen, for example, the lightest element is made up of a single proton. There's also a heavy form of hydrogen called deuterium, which is a single proton, single neutron. The next heaviest stable element of is helium. Helium's got 2 protons in it, but it could have 2 protons and 1 neutron. It's helium-3, or more commonly 2 protons, 2 neutrons, helium-4. Next element of is lithium, lithium-6 and lithium-7. The next one is beryllium-9, boron-10, boron-11, carbon-12, carbon-13, and so on and so forth. What is slightly interesting, though, is they are all the stable forms of matter that we see around us, but we can also make radioactive forms of all of those elements. And we spent a lot of time doing these. Tritium is one of the first radioactive forms of hydrogen, and these little combinations of light particles added on, or with protons or neutrons pulled away from atomic nuclei, form radioactive forms of these elements. And if we look at that over the whole periodic table, we can build up this big chart of all of the possible combinations of protons and neutrons that make up everyday life. That make up nature as we know it. The black squares on this little plot here correspond to the combinations of protons and neutrons that form stable material that make up everyday life. Blue squares on here correspond to radioactive species that have been identified that decay by something called beta plus emission. The purple ones decay by something called beta minus emission. The yellow ones correspond to materials that radioactively decay by something called alpha emission. And the green ones correspond to nuclear fission. So lots and lots of combinations of radioactive material have been measured so far, over 3,000 in fact, in the laboratory, and only something like 300 of those combinations make stable forms of matter that make up everyday life. Most of those radioactive forms only exist for a fraction of a second, but they're crucially important that we understand how they're made and where they come from and what their properties are, because it turns out that we now understand, or we now propose, that the production of those radioactive forms of material in things like nuclear explosions in stars are the precursors to help form the stable isotopes or stable elements that we observe around us in nature. So there's a whole bunch of other related questions linked to nuclear physics that we can try and answer, and are still big questions now. One is, what are the limits of existence? Is there a top to the periodic table? Is there a maximum number of elements that we can create? Is there a maximum range of isotopes that we can create? Is there a range in the number of protons and neutrons that we can add together, even if it only lives for a fraction of a second? What exists? What limit does nature put on those possible combinations? Another one is, what's the effect of these limits of stability on so-called nucleosynthesis? Nucleosynthesis means the creation of stable elements in stars, usually, or we think in stars or stellar explosion. And also, just from a fundamental science point of view, we really want to know about the force that holds the atomic nucleus together. Can we tell anything about what the shape of the nucleus is? Do we imagine they're all spherical, like a little ball, like a liquid drop? And there's quite a lot of experimental evidence that suggests that many nuclei have very strange and exotic and unusual shapes, maybe look like rugby footballs or pears. If they do look like that, can we understand why they would look like that? Is that related to the nature of the force that holds the protons and neutrons together in the nucleus? So I've just flashed it up. That's a picture of I said we're going to try and measure the smallest things, but actually this is relevant for some of the biggest things. That's an example of a supernova, big supernova, the death of a massive star, an explosive massive star. And that picture is taken by the Anglo-Australian telescope, luckily searching through the night sky in 1987, so before all of you guys were born. And then maybe a couple of days later, after searching through the same bit of the night sky, you can see there's one of those stars has an enormous amount of light emitting out from it. And we now understand that to be an explosion basically called a type 2 supernova. And that was the first sort of obvious, easy to find, identify laboratory that we might be able to look and identify emissions of that told us about characteristic elements being formed, and give us a little test as to see whether the material we were looking at in our laboratories here was also being formed in these, death in this case of massive stars. So the upshot is, what we try and do is, in quantum mechanics, we understand that atomic nuclei can radioactively decay. They've got specific half-lives associated with them. And if we're lucky, they radioactively decay to excited quantum states in their daughter nuclei. So I've got an example here of this nucleus, potassium-40. It's in you, it's in your bones. It makes up a lot of normal potassium. It's interesting, it's got a half-life of 1.2 billion years. That means the stuff that we are seeing now of potassium-40, any bit of salt that you might have, or sea salt, which has got potassium in it, was here when the Earth was created. And it's taken 1.3 billion years on average to radioactively decay. And it has a nice signature if it radioactively decays. It radioactively decays to two types of elements, because it can radioactively decay by both beta plus and beta minus decay, and electron capture. So it predominantly decays to this nucleus, calcium-40, but about 10% of the time it radioactively decays to this element here, argon-40, a gas nucleus. And when it does decay to that argon-40, it actually decays to what they call an excited quantum state in argon-40, which has got this energy, 1460.9 in the units we would use kilo electron volts above the ground state, above the lowest energy in argon-40. And that's emitted in the form of a blast of light called a gamma ray, which your eyes can't see. And this lecture, or the lecture you're going to see, is how we measure those gamma rays, how we can see those gamma rays, how we can identify them. And that gives rise, hopefully, to show you a huge amount of information, lots and lots of useful applications of nuclear physics, which you'll also get from the same lecture. So I hope that could be a little flavour of what we're going to try and do, and I look forward to seeing you online in a week or so's time. Thank you. Bye.